Good evening, my name is Gonzo, and this is the final of the 3 videos we are doing on soccer modeling in Python from scratch. Today what we're going to do is we are going to look at, in our strategy, how do we know when to bet and what is the optimal amount to do so. So, where we were last time is we have taken the pinnacle odds and we have removed the overround from those odds. So we now have 3 new columns in our data frame. We have pinnacle true home prob, pinnacle draw prob, pinnacle true away prob. And to check whether or not we had got that correct, we added all 3 of those columns up to get the total probability. The first thing that we're going to do is we're going to do some light housekeeping to make all of this code reasonably nice, and then we're going to get on with figuring out when we should bet. Right then, let's make that a little bit smaller, move that across to there, and we need to get rid of the cruft and we need to make this lovely. So we import everything in, we do this garbage here, we can get rid of main df here, it's not doing anything. Let's get rid of that. This was demonstration code from the last one. That's demonstration code. This is demonstration code, so we can get rid of that. We can get rid of this because that's demonstration code. So what we need to do is we now need to take out the things that we need, and we're going to put them into the appropriate place in our code. So when I format code, I really quite like to have the functions that get called at the top, so I know what I have, like the tools that I'm playing with, and then the rest of the sort of functional things from there. So we're going to take find true probabilities equal, and we are going to cut that and put it, let's put it in a new cell just below these guys, because that keeps the functional code away from the sort of procedural script stuff. Then what we're going to do is take this piece of code here, which is the one that creates the 3 columns for pinnacle true home, pinnacle true draw, and pinnacle true away, and we're going to move that to underneath just here, like that, because at this point we should have our main df, then we're going to add these 3 columns that we want. Let's keep this line so that we know that we've done things correctly. And actually what we're going to do is we'll put in some, are we going to put in a test? Yes, what we're going to do is we're going to put in a test in a second to make sure that everything is correct. I'll show you how that works in a moment, and it's something I like to do as we're going along, especially when our data science code gets a little more sophisticated and we get closer to something that feels like production code. We are a long way from production here. This is very much just exploration. But as we edge towards production, it's good to put in points where you know something to be true. Small jump cut because OBS crashed. It's been doing that a lot lately. I need to figure that one out. Doesn't matter. Let me show you where we are. So we have this cell here, which imports everything, sets a couple of options. Then we have this cell here, which gives us the find true probabilities equal. Then we have the season list, all that stuff. And then we've got the creation of our main df down here. What we are going to do is a thing where we're going to restart the kernel and clear the values of all cells. Run it, and we'll aggregate where we're at. So we import everything. We're going to define that function. Then we run through all of the data and create our main df. Then what we're going to do is do the pinnacle math on top of the things that we want. And then let's just have a look at main df. This feels good to me. I promised that we were going to put some light testing in. So what we want to do is we want to find out what is the length of the main df where main df totes does not equal 1, and that should be 0. So if we run that code, it says 657. This is why we do these checks. Let's go and look for those. Where is main df totes does not equal 1? Let's have a look at them. If we look at those, it gives us these things here. So this is worth an investigation as to what is going on here. It feels correct, and what is probably happening is that some floating point shenaniganery is occurring. I was correct. Some floating point shenaniganery is occurring. So if we look at all of the data where the totes is not equal to 1, it claims that it is 1 out here, because in this column, pandas for display purposes is doing some rounding. And if you actually pull out a value from there, so we're using a .loc indexer here because this first row has the index of 4. So if we use the .loc index and pull out the actual value for that column, we see it's near as damn it 1. So what we've got to do is just very quickly round this to 1 in order to be able to do our check. So the way that we're going to deal with this is we are going to apply a mask. So basically we know that everything that's within a very tiny floating point error we want to kind of ignore. That's fine. We should be rounding that to 1. If something is very well outside that floating point error, then we want to reject it. So if it's like 0.8 or something like that, we know we've done some of our maths wrong. This isn't strictly helping us with our model, by the way. This is just like good practice for production later on. So we're going to create a tolerance. And the tolerance is going to be 1e minus 7 feels good. Okay, so what that means is that we've got to be within 0.0000001 of 1 in order to be able to pass this test. And then we need to create ourselves a mask. So the mask will be np dot. We're interested in if it's the absolute value. So is it above or below the line? So 0.99999 is okay, and 1.0000001 is okay. Everything else we're going to try and reject. So at that point, we want to say that this is main df where totes -1 is probably the way we should do this, is less than or greater than? Yeah, less than or equal to the tolerance. Aces. What we're then going to do is we're going to assert that the len of the main df where we are not applying the mask equals 0. And that passes. Okay, actually we can look at this len specifically. So what assert does is it just claims that something is true, and then it rejects you. It throws an error if it's false. So if we were to say that this is actually 1, you can see we get an assertion error. And we can be fancy, right? You can be fancy, and you can put in, you need a comma here. You can put in some kind of message here. So you could say like calculations are not correct. And then that gives you a nice error that looks like this, but we're not going to do that. Okay, we're just going to say we're going to assert that it is 0. And in order to tidy up our code, what we're going to do is we're going to copy this bit and we're going to put it just here. Because then what we can do is we can do these calculations, and this assertion error will trip if we have in some way done them wrong. This is good for when we're going to add more data later. I've done some light tidying up so that the code now runs from top to bottom. And what we're going to do now is we're going to get into the actual meat of what we're going to talk about today, which is expected value and the Kelly criterion. We'll deal with these one at a time, but first let's talk about expected value. So the expected value in any given bet, and the formula for it is highlighted just here. Let me get my pointing correct. This is an article that you can go to. It's by the Pinnacle bookmaker about what expected value is. It's fundamentally the amount of money that you could expect to win on average per bet if you were to make that bet over and over and over again. We are looking for, in general, plus EV expected value strategies. We are looking to maximize the amount of value that you make from a bet. A really good example of this, the canonical academic example, is if somebody gives you better than 2 to 1 on a coin flip. So if somebody says, listen, if it comes up heads, I'll pay out 3 to 1, but I'm going to keep your money if it comes up tails. 50% of the time it will come up heads, and you will triple your money at that point. So this is a plus EV bet. Although for any individual event, you are not going to be able to predict which way it goes. And in sports betting, this is kind of like in general how it works, or in any kind of betting actually, whether you're doing like GTO poker or whatever it happens to be. Fundamentally, for any given event, I can ascribe a range of probabilities as to what will happen, but I can't tell you with any degree of certainty what the outcome of that one event will be. However, what I can say is that if I continue to make plus EV decisions. I can make bulk predictions about events over time. Anyhow, as I say, this is the formula, the probability of winning times the amount won per bet minus the probability of losing times the amount lost per bet, and we are going to replicate that in Python. In order to be able to do this, what we're going to do is write ourselves a convenience function, because we're going to use this over and over again. So let's set ourselves up and get that done. So what we want to do is we want to, oops, sorry, I was writing inside my notes and not in my code. So we're going to write ourselves a function. So let's say we're going to calculate the expected value of a bet from the odds, because that's what we're going to do. We're going to calculate the expected value from the odds, and we're going to take in the bookmaker odds and the probability that we think of this event. So our opinion in the market. So your I'll say our probability. And we're going to return the expected value. And the expected value will just be a number. It will be like 0.1 or 0.6 or 1.1 or whatever it happens to be. So the payout is the bookmaker odds. And the EV is our probability minus, multiplied by the payout, minus 1. And this is a rearrangement of the other formula. So if you take this formula here and you rearrange for expected value, then that's what this is. Yes, the reason that we're slightly different to this is that this uses the probability of winning. So our opinion of probability multiplied by the bookmaker's odds minus the probability of losing multiplied by the amount lost per bet. And if you rearrange that, this thing here occurs. And I've just noticed that probability. Return EV. Okay, so let's just check it. All right, so we want to calculate, we know, okay, from just knowing things about gambling, that if we are given odds of 2.0 on a coin flip, then the expected value of that bet is 0. So if the bookmaker odds are 2.0 and the probability of the event is 0.5, then we get what we want. And we could even put in a small test here, right? We could even say that I want to assert that this equals 0. You could do that if you wanted to. You could start to add tests as you go along. Let's just also check that the situation that I was talking about comes true as well. So if somebody gave you 3.0 on a coin flip, that would be very bad for them, because we would have a expected value of 0.5 or 50%. So for any 1 unit of currency that we staked on this bet, we would expect to win 50 cents in profit every single time. But we can go one step further. So a while back, and by a while back, I mean the mid-50s, some dude called Kelly, actually reading his article, he was called John Larry Kelly Jr., got really into the mathematics of gambling. In particular, he was a blackjack player, and he was interested in how much you should stake if you think you know your advantage. What is the optimal amount of money to stake on something in order to be able to grow your bankroll? And he came up with a thing called the Kelly criterion, which is, there's a Wikipedia article on it right here. The thing that we're interested in is this here, which is the formula that tells us how much of our bankroll we should be staking at any one time on an event where we have a reasonable idea of the outcome. Now, it's not a perfect formula for us, because the Kelly criterion makes a key assumption that we cannot make, which is that you actually know with certainty what your edge is. As a result, we will treat the Kelly criterion with some caution. We are not going to go into where this formula comes from. If you are horrendously interested in it, you can read this, okay? Fundamentally, what you're doing is you are maximizing the logarithm of wealth in your bankroll. Way beyond the scope of this video. If you can read this, good luck to you. But what we can do is we can put it into our code. We can use that formula and figure out, given a bankroll and an expected value and some odds and a thing we call the Kelly fraction for reasons that we'll come on to in a second, how much should we be betting? Now, I'm going to do a thing that we've done before, which is I'm going to copy and paste the function in so that I can talk it through and I won't make a mistake while I'm talking it through. So this is the function that will give us the Kelly criterion. It's here. So it's calculate Kelly stake. And what it takes in is it takes in a bankroll, an expected value, the odds that we are offered, and a thing we're going to call the Kelly fraction. And we'll give the Kelly fraction a default setting in a second, but for now, let's just ignore it. We do a quick check. So if the odds are less than 1 or the Kelly fraction is less than 0, let's just leave it alone. Okay, return 0. Something has clearly gone terribly, terribly wrong. This is the kind of thing you might put in if you can't trust your data, which we can't 100% trust this data source. It was free. When we get out into like the wilder leagues, some of the data is just going to be incorrect. And so we'll stick this in. This tells you how much of your bankroll, what fraction of your bankroll should you be staking. So we take the expected value and we divide it by the odds minus 1. That is a rearrangement of the formula that we saw earlier, this one. If the stake fraction is less than 0, so if we have negative EV, basically, then don't stake anything. Or actually, as well as if it's 0. So if we're being offered 50-50 odds on a coin flip, don't take that bet. There's no point to it. We don't bet recreationally. We only bet to make money. So don't make that bet. Then we multiply that stake fraction by the Kelly fraction. And then we multiply the stake fraction by the bankroll to tell us how much money to actually bet. Now, the Kelly fraction is there because the full Kelly is kind of a wild ride. Like, it's not uncommon in sports modeling terms to have for your model to predict quite a wild EV. And you can do one of two things with that. You can throw it away, or you can moderate the amount that your model predicts to bet. Because sometimes you might find that your model is like, hey, you should be betting 50% of your bankroll right now. And that might be the mathematically optimal thing to do, because if you were to simulate that whole process infinitely, then that makes the most money across all simulations. But that's not what we want to do right now, because we don't just want to like show up and wager 50% of our bankroll. So frequently what you will find in the sports modeling space is that people moderate the amount of money they bet. So a common Kelly fraction is to say, do you know what? Let's take what Kelly says with a grain of salt and bet 1/4 of it. So we're going to put that as the default value for now. We'll muck about with it if it becomes a problem later. So what we want to do now is we want to add a column to our data frame that gives us the expected value of any given bet. Remember, we are taking the pinnacle true home probability. Oh, we're only going to look at home things to start with. Let's just look at home game. Look at the home odds. We're going to take the pinnacle true home prob as our actual probability, and then we're going to look at the home max odds. What could we have got away with betting on? So let me consult my notes. Like last time, we're going to use main.df.apply. So let's just home EV is equal to main.df.apply, and we're going to use a lambda function again. So let's just make sure we're all okay. So lambda, I'm going to take in a row, and we're going to use calculate EV from odds. And that function will take in the row's home max odds as that which we could bet on. So remember, the calculate EV from odds takes in the bookmaker odds and then our probability, which means that we should also take in the row pinnacle true home prob, I think it's called. Let's just check that before we do anything. We need to put a comma in there, and axis equals 1. Before we go wild, let's just have a quick look at main.df.head and double check that we've got that right. I'm interested in the naming. Pinnacle true home prob. Yeah, that's fine. Pinnacle true home prob. Cool. Get rid of that. Okay. Inspecting main.df.head. What can we see? We see, as you'd sort of expect in the home EV column, lots of negatives, which is probably what we'd expect, right? Bookmakers don't like to give away expected value, and this feels more comfortable, okay? Let's just have a quick look and see if we've got any column rows at all. where we might consider betting. Oh, and we do. Cool. So we've got 184 rows of plus EV. It's not a lot. Maybe we'll have to bring in some more data to make this model really sing, but let's, go from here. So, final thing. Let us apply the Kelly criterion to our data that we have and see if we can come up with a plus EV strategy. Let's see if this works. Now, the Kelly criterion is a little bit different because it depends on what happened before it, right? So we're going to have to iterate through our events. We're going to have to work through the bankroll. Sorry, not work through the bankroll. We're going to have to work through the matches and take them one at a time. So we're going to have to start with the bankroll. So unlike previously where we started at 0 units of currency, we're going to have to start at some notional amount. So let's start at 100 because that feels good. Because remember, we are ultimately going to be making a decision about how much to bet, and that depends on how much is actually in our bankroll itself. So we're going to have to iterate over the entire data frame. So for I in range len main df, we are going to have to actually physically iterate over each of the rows. The first thing that we want to find out is what is our bet size. So our bet size is equal to calculate the Kelly stake, that one, and we want to take our bankroll at the time, and then we want to take the expected value, which is the main df dot loc I. So what row are we on? And it's the home EV. Then we want to take the odds, which are main df dot loc I home max odds. And then let's leave the Kelly fraction. Oh, excuse me. Hang on. Let me scroll so you can see it. Let's leave the Kelly fraction as it is for now. We can go spicier if we need to, but let's leave it where we are for now. So that gives us our bet size. And then what I want to do is I want to go ahead and write that down in the... Just we'll write that down in the data frame. Just main df dot loc I. Note the different syntax for recording something in a data frame as opposed to reading it in. You use one set of square brackets rather than two. That is equal to bet size. I'm just going to write that down in case we need it later. I'm not sure that we do, but I can't remember. Right, so and then what we do, the first thing that happens when you make a bet is that you subtract bankroll equals bankroll minus bet size. You just subtract the amount of money that you're going to bet from your bankroll. That's what physically happens when you go to a bookie. They take your money off you, and then, depending on what happens, you might get some of it back. Who knows? Okay, then we want to know if the home team won. So if the main df dot loc I full-time home goals is greater than main df dot loc I full-time away goals, then our bankroll increases. So at that point you win the bet, right? Bankroll equals bankroll plus bet size multiplied by home bet df. No, not home bet df. Sorry, that's what it's called in my notes. Main df dot loc I home max odds. This represents us winning. If we don't win, then we just don't get our money back. So that subtraction just happens. So we've given away our money, and then here we win it back if the full-time home goals is greater than the full-time away goals. What we're going to do is we're going to record our bankroll. So main df dot loc I comma bankroll equals bankroll. And what I want to do then, main df dot plot, oh no, sorry, dot bankroll dot plot. And let's have a look at the graph. I mean, it's not nothing. It's not knocking your socks off, but it's not nothing. Okay, so the strategy has survived 2,000 opportunities to bet and not decided to do so in very many cases. Okay, so we've got over 2,000 opportunities to bet, and we only decided to do that, I think, in 183 cases. So we've bet 183 times, and we have won just over 1 unit of currency, which you and I might look at and go, well, not even sure why we showed up. Now, there are a few things we can change in order to be able to figure out what is going on. Now, 183 is not a very large sample size, but also the first thing we can do is we can increase the Kelly fraction. So let's just take a look at what happens if we increase the Kelly fraction. Now that means that the losses are bigger, but also the gains are bigger. So we've gone up to 104 units of currency, but we scoop down to about 90 at some point as well. Remember also, we've only considered home games, right? We've only considered betting on the home team. If we were going to expand out this model, which we probably will do in future episodes, I'm not going to exactly do that now because there's one other thing we can do just to expand out all of the information that we have, which is to bring in more data and just look at the applicability of this across more matches. Another of the things that you can do is you can look at each position and decide which position has the best EV and then bet on that one. That requires some slightly more complicated logic in the back test, but it's representative of a more realistic position, right? You would look at the home EV, the draw EV, and the away EV, and then you would bet on whichever had the most EV. For now, though, we have only had 183 opportunities to bet. So what we're going to do is we're going to bring in a whole load more data. So let me adapt right at the top here this function that we had. So when we gathered in our data, we had a season list and a league list, and well, actually, sorry, it's not a league list, it's a league. And so what we're going to do is we're going to turn this into a list, and then we are going to iterate over it. Right then. So for league, in league list, we're going to do something, and we're going to need to rename this to league list. And we are going to have to do this and push that out. So now we're going to iterate over every league, we're going to iterate over every season, and we are going to read in the CSV from there, and then we're going to add those to our data frame. We don't need to make any other changes to our code because we already sort by date, we already read in the bookmakers that we need, and we reset the index down here. So let's just reset the kernel and check that this works. So if we reset the kernel, clear all outputs, let's just run all of our code just to make sure that we haven't made a mistake. So we run that, run that, run that, let's run that. So our assertion holds true. We're going to calculate the EV from odds. We don't have to assert that. Let's get rid of this piece of cruft. We're going to calculate the Kelly stake. We're going to run through our main DF, and we should get exactly the same as before. Aces, that's fine. What we'll do now is I'm going to bring in all of the leagues I know about. So this list, I'm actually going to let you pause at this moment and then look at it. But this is the list of all of the leagues. So armed with all of these leagues, and actually let's push out the data that we get. So let's all go from 16, 17. So 16, 17, 17, 18, 18, 19. Right, that's getting us everything from 2016, 2017, 18, 18, 19, 19, 20, 20, 21. Yep, right, bro. So now we're getting everything for all of these leagues from 2016 to 2025. So if we run all of this, let's just restart the kernel. And run everything. This is going to take a moment. There will be a jump cut. And immediately there was a problem. Now, this is a problem that I've actually sorted out, so bear with me. Let's talk it through. So not all of the data is in the same format. If you ran the code that I just gave you, you will have immediately got an error. Actually, not immediately. After a frustratingly long time where it loads in the data and then finds that it's in an inconsistent format. So let me talk about the things that you have to do to make all of these CSVs play nicely with each other. The very first thing you have to do is just here, under the data URL, you need to read in two different ways because the way that Joseph Buchdahl has saved this data is inconsistent. Encoding is not something we're going to talk about right now, but basically the two files have been saved slightly differently. So you need to try and accept. This is Python like doing error handling. So you can try one thing, and if that doesn't work, do something else. And this is what's happening here. So we read in the data using the read CSV that we've always used. And if that doesn't work, then go ahead and try it with the Latin encoding. Like I say, we're not going to get into what exactly that means, but basically the file is saved in a slightly different way. Then the dates have a problem with them. So when we come to parse the dates, we need to try in two different ways. So we need to try to parse the data frame like the dates like this. And if that doesn't work, then try mixed. I don't think we actually strictly need this. I think we're going to fall back because of the way this is written. We're going to concat every time. So actually, we don't need this. Okay, sorry, I've misled you. We can get rid of this. We just try, just do this. The format of the dates is mixed. You figure it out, pandas. You have a go. So when you read all of this in, which I have done, you're going to find that you get a warning to say that you've got lots of data frames joined together, Chief. Be careful out there, and that's true. We then run everything through, and here we have to do something else. So here we have to drop, not all of the data is complete, so some of the data frame, some of the data that we've read in, specifically from like the wilder leagues, like the Turkish League and the Greek League from 2016 and stuff like that, they don't have complete data. So where we don't have a pinnacle odd, just drop it. Okay, where we don't have the odds for pinnacle, I'm not interested. I wouldn't have bet. So get rid of it, out the door. So we drop those. So what we're going to do is use this functionality here, which is that we are going to, where the data frame is NA, I want the opposite of that, which is what the tilde is doing just here. Then we need to reset the index. Remember, resetting an index is important for two reasons. One, because we're going to use it later on. And two, because we can use it for our bankroll. They're actually the same reason. My apologies. Resetting is important. Then we run through everything as you have seen before. We're going to calculate the EV from the odds. And this is where this line becomes really important. Like this was the warning that made me put these things in, actually. So this thing here tripped, and I was like, wait, why is it tripped? And so I found out that this was wrong, and I had to do that. We calculate the Kelly stake as normal, the home EV gets applied, and then we can run this. And this is the graph that you will find. So we had 60,000 opportunities to bet, and we made, in the back test, around about, we multiplied our initial bankroll by 8. It's tailed off recently, but we multiplied our initial bankroll by 8. We started with 100, and now we have 800, or just shy of 800. You can get wilder, and let's just show you the impact of the Kelly stake. So I took off I'm using the default here, which is 1/4 Kelly. If you go out to the full Kelly, watch what happens. Gets pretty wild out here if you go out to the full Kelly. It will go up to like 70,000 if I remember correctly. It's taking a mo because it's chewing through all this data. If you go the full Kelly, remember, you have to be comfortable with the fact that the swings are huge. You will make lots of money, but you also lose lots of money, because at some point this model is going to be like, hey, you should bet like a third or a half your damn bankroll. And at that point, you're in trouble. Yeah, see, here we go. So if you go the full Kelly, and this is exploring the power of Kelly, right? If you go the full Kelly, at some point we would have started with $100, and we would now have $70,000, and then we would have lost nearly half of it in the last, like, whatever this is. I haven't got dates associated with this. There are ways you can extend this, and I invite you to. All right, we're going to stop here for now. But there are ways that you can extend this. You could look at the draw EV and the away EV. You could look at, if you go into my GitHub, which I will link in this video, and I'll put this code there. But if you go to my GitHub, there is also a repository called Football Stats, which has in it, let me show you everything that's in there. I am using, from my notes, this notebook here that's in Football Stats called Better Than Pinnacle. And in Better Than Pinnacle, which is exactly what I've just walked you through, there is a function somewhere, there is some code, which walks through what do you do when, I can't find it right now. Anyway, it's in there somewhere. What do you do, like, how would you normally conduct yourself? Because normally what you would do is you would come to a game and you'd be like, which has the greatest EV? The draw, the home, or the away? And then you would pick the one that had the greatest EV. You don't always bet on the home, or always bet on the draw, or always bet on the away. You pick which one, like, you actually want to bet on, and that is a better way of backtesting it. We are going to stop here. This has been a good series, but we're going to stop here. If there's more stuff that you want to see, let me know. I'm going to trundle on in my own way. We're going to make things like this better. We're going to do a bit of a light intro to data science, and we're going to look at the Poisson model next, I think, actually. Let's look at, if we're not going to use other people's statistics, how could we model a sporting event? It's significantly harder than you think, and we may not actually come up with a plus EV model, but we'll get down the road some way to doing so. Anyway, my name is Gonzo. You should follow and subscribe for more of this.